viewers, in our ongoing series on reactive methylene compounds, we had discussed Claisian ester condensation for preparation of ethyl acetoacetate. We had also discussed keto-enol tautomerism. Reactions of keto-enol form of ethyl acetoacetate were discussed at great length. We know that ethyl acetoacetate exists as a tautomeric mixture of keto and enol forms. As you can see on your screens, the left hand figure depicts the keto form, right hand depicts the enol form. These two exist in dynamic equilibrium in solution, where the keto form exists as 90% and the percentage of enol form is 10%. In our previous discussion, we had also discussed the reactions of these two forms. For that, you can refer to the link shown on your screens, that is tautomerism in ethyl acetoacetate. And it would be great if you listen to the reactions of the ethyl acetoacetate because of the keto form and of the enol form. Now let us discuss the reactions which make ethyl acetoacetate a useful synthetic reagent. But before going on to discussion of on the synthetic characteristics of ethyl acetoacetate, I would like to discuss the acidity of methylene hydrogens. That is, ethyl acetoacetate is a reactive methylene compound in which the methylene group is sandwiched between two electron withdrawing groups. Now you may ask yourselves a question, why is there the need to discuss again the reactions of the reactive methylene group? So we know that ethyl acetoacetate contains a reactive methylene group, a group that is sandwiched between two electron withdrawing carbonyl groups. The CH bond in CH2 group is highly ionizable since the removal of proton results in the formation of stable carb anion. Why is this happening? Because as you can see on your screens, the methylene group is sandwiched between the aceto group on one side and by an ester group on the other side. And these two groups are electron withdrawing groups. That is, they have the tendency to pull the electrons towards themselves, as a result of which the bond between the methylene carbon and the hydrogen becomes weak, and this hydrogen is eliminated as proton. So in other words, we say that the hydrogens of the methylene group are acidic in nature. So the acidity of the CH bond of the methylene group can be explained on the basis of two factors, which I had discussed in one of my earlier lectures also. But I would like to recapitulate here, because it is the reactions of the methylene group, that is the reactions of the acidic hydrogens, because of which ethyl acetoacetate is so widely used as a synthetic reagent. So the acidity of the CH bond of methylene group can be explained on the basis of two factors. The first is the inductive effect. You know, this effect is caused by the electron attracting power of the electronegative oxygens of the two carbonyl groups between which the methylene group is sandwiched. And the electron withdrawing effect of these two groups weakens the bond between carbon and the hydrogen, and this hydrogen atom dissociates to give a stable anion. This you can again see on your screens, that the two carbonyl groups are withdrawing electrons towards themselves because they are more electronegative. So as a result of which the methylene carbon also becomes electron deficient. Now since it is electron division, the methylene carbon, and it is slightly more electronegative than hydrogen. So it will pull the electrons towards itself, as a result of which the bond between the methylene carbon and the hydrogen becomes weak, and this hydrogen is given off as proton, resulting in the formation of stable carbon ion. So condition number 1 is, and why is this now carbon ion stable? This is stable, or the stability of the carbon ion can be explained on the basis of resonance stabilization. That is, the acidity of CH bond is greatly increased because the negative charge in the carbon ion is delocalized into 2 carbonyl groups by resonance. This you can again see on your screens. That is, the first structure is the one which we are getting, the topmost structure, which we are getting due to elimination of hydrogen as proton. That is, we are getting a carbon ion. Now this carbon ion can undergo resonance because of interaction of the negative charge on carbon and the double bond of the carbonyl group of the aceto group. And the next resonating structure we can get because of interaction of the negative charge on the methylene carbon with the aceto group of the ester group, the carbonyl group of the ester group. So what we find here is that the negative charge is delocalized over oxygen, methylene carbon, and the oxygen, that is oxygen, carbon, carbon, oxygen. So the resonance hybrid is highly stable because the negative charge is delocalized over more electronegative oxygens. So as a result of the formation of stable carbon ion, now what we find that this carbon ion or the enolate ion has a tendency to form salts. So before going on to discussion on how does ethyl acetoacetate act as a synthetic reagents, let us first discuss 3 important reactions of ethyl acetoacetate because of the presence of acetic hydrogen. And these 3 reactions we will be generally using in all the synthetic applications of ethyl acetoacetate. First reaction is the salt formation. As we already know that the hydrogen of the reactive methylene group is acidic in nature. So when it is ethyl acetoacetate is treated with a strong base like sodium ethyl oxide, it forms a sodium salt. This you can see again on your screens, that ethyl acetoacetate reacts with sodium ethyl oxide, resulting in the formation of sodium ethyl acetoacetate. And what happens during this reaction is an ionic bond is being formed between the methylene carbon and sodium. Here you will notice that there is no bond, the covalent bond between carbon and hydrogen, the methylene carbon and the sodium, because we have a negative charge on the methylene carbon and we have a positive charge on sodium. So this bond is ionic in nature, which is being depicted by a negative charge on methylene carbon and a positive charge on sodium. Now the first thing which happens is the formation of salt. Now after salt formation takes place, this molecule can now undergo alkylation by nucleophilic substitution reaction, and the mechanism of the nucleophilic substitution reaction is going to be SN2, that is bimolecular nucleophilic substitution reaction, in which the ester anion as well as the alkyl halide will take part in the reaction. So what we find in this case, that ester anion acts as a nucleophile and it makes a bond with the R. So with the alkyl group. So what we find in alkyl halide, bromine being more electronegative than the alkyl group, will pull the electrons towards itself, as a result of which the alkyl carbon will have a partial positive charge And what we are noticing here on, as you can see on your screens, that ester anion has a negative charge on methylene carbon. So it will act as a nucleophile through this carbon and make a bond with the alkyl group, resulting in the formation of alkyl acetoacetic ester. And sodium and will react with bromine, resulting in the formation of sodium bromide. So when we can now do two more reactions with this molecule, that is, we can do acid hydrolysis or we can do the ketonic hydrolysis. So if we want to convert directly ethyl acetoacetate into its derivative, we will just convert it into its ester anion and then carry out the reaction. But if we want to prepare a derivative of ethyl acetoacetate, then after preparing the ester anion, we will carry out a nucleophilic substitution with the desired compound, which can be an alkyl halide, to get the derivatized alkyl acetoacetic ester, which can then undergo further reactions. So the next reaction, which is very important, is ketonic hydrolysis. Why is it known as ketonic hydrolysis? Because when reaction is carried out with dilute HCl, it will give acetoacetic ester. Acetoacetic ester will yield a ketone. So since we are getting a ketone in this reaction, it is known as ketonic hydrolysis. In this reaction, acetoacetic acid on heating undergoes decarboxylation to form acetone. So what you have to remember is that when we are carrying out the first reaction, in the first step when we are carrying out ketonic hydrolysis, ethyl acetoacetate on hydrolysis with dilute hydrochloric acid yields acetoacetic acid. And this acetoacetic acid on heating undergoes decarboxylation to form acetone. And as I've already said, because on hydrolysis, acid hydrolysis, dilute acid hydrolysis, we are getting of ethyl acetoacetate, we are getting a ketone. This reaction is known as ketonic hydrolysis. As you can see, the reaction of ethyl acetoacetate on hydrolysis gives us acetoacetic acid, and this acetoacetic acid on heating gives us acetone. So what you can now visualize is that when in the first reaction, hydrolysis of ester is taking place, resulting in the formation of acetoacetic acid and ethanol. And in the next step, this acetoacetic acid on heating undergoes decarboxylation, that is, a molecule of carbon dioxide is lost and acetone is being formed here. We will in the future be discussing how do we bring about the simple ketonic hydrolysis of ethyl acetoacetate. The second type of hydrolysis which we can bring about is acid hydrolysis. And acid hydrolysis is carried out with concentrated NaOH in presence of dilute HCl when acetic acid is formed. And you can see on your screens here, it has been simplified for you. That is, you have to remember that when you are carrying out this reaction, we will bring about this reaction with the help of two molecules of water. And what you have to remember is that the carbonyl carbon is electron deficient. So OH will go to this carbon, resulting in the formation of acetic acid, and H will add to methylene group, resulting in the formation of CH3. Then in the next step, what happens is H goes on to CO and OH goes on to C2H5. Or to make it simple, what you have to remember is that you will break the bond between the carbonyl carbon on the left hand side and the methylene group. And you will break the bond between the carbonyl carbon again of the ester group, and we will add OH to it, and H will go on to the C2H5O group, resulting in the formation of two molecules of acetic acid and one molecule of ethanol. So all these four reactions that we've discussed till now, that is, first was converting ethyl acetoacetate into its sodium salt. Then we can bring about directly ketonic hydrolysis if we want to convert ethyl acetoacetate into acetone, or we can bring about acetic hydrolysis if we want to convert ethyl acetoacetate into acetic acid. But if we need derivatives of ethyl acetoacetate, that we want to make propanoic acid or we want to make butanoic acid, then the modification will be done here. That is, the sodium salt of ethyl acetoacetate will be treated with a alkyl halide, which will then be made to undergo acetic hydrolysis when we will get the desired acid. So now let us look into the synthetic applications of ethyl acetoacetate. And what we find that ethyl acetoacetate can be used in the synthesis of carboxylic acids, and these carboxylic acids may be simple carboxylic acids, they may be dialkyl carboxylic acids, they may be high carboxylic acids, they may be dicarboxylic acids, or they may be unsaturated carboxylic acids. Then we can also prepare ketones from them, from ethyl acetoacetate. Alicyclic compounds can also be prepared, and heterocyclic compounds can also be prepared from ethyl acetoacetate. Therefore, one says that ethyl acetoacetate is a very important synthetic reagent. So let us now discuss the synthesis of alkyl acetic acids. So when we are carrying out the synthesis of alkyl acetic acid, this reaction will involve the reaction of sodium ethyl acetoacetate with an alkyl halide followed by an acid hydrolysis. So that means in the first step what we are going to do, we are going to convert ethyl acetoacetate into its sodium salt. Then we will carry out the reaction with the alkyl halide. When we will get alkyl derivative of ethyl acetoacetate, and this molecule on hydrolysis, that is acetic hydrolysis, hydrolysis with concentrated KOH in presence of dilute HCl will give us the desired alkyl acetic acid. So as you can see on your screens here, the ethyl acetoacetate is treated with sodium ethyl oxide when the sodium salt of ethyl acetoacetate is being formed. This on reaction with an alkyl halide can be bromide or iodide, we get a alkyl substituted ethyl acetoacetate, and this on acetic hydrolysis will give us one molecule of acetic acid and one molecule of alkyl acetic acid. So as you can see on your screens, I am repeating what I have said previously. To make the reaction simple, you will break the bond between the carbonyl carbon on the left hand side and the methylene group. When you do that and you will add OH to the carbonyl carbon, since that carbon is electron deficient, and on the right hand side you will again break a bond, and between the CO, the ester group, and the OH will go to C2H5, when you will get acetic acid and the alkyl acetic acid plus C2H5OH. So from where are we getting this alkyl acetic acid? We are getting it from the methylene group and the ester group. By the hydrolysis of the ester group, you are getting alkyl acetic acid. So let us now look into the preparation of butyric acid. So what are you going to do in this reaction? Butyric acid. So how many carbons are we getting from ethyl acetoacetate? You are getting 2 carbons, 2 carbon atoms. One is this carbon atom, the Ca methylene carbon, and the other one is the carbonyl carbon. And we know butyric acid has 4 carbons in it. So if butyric acid has 4 carbons in it, that means we are short of 2 carbons. So what is the alkyl group that we need to introduce here? 4 minus 2 gives us 2. That means we need to do the reaction with ethyl halide, and that ethyl halide can be ethyl iodide. So first of all, you are going to look into the structure when they give you a conversion like this. That is what are they asking you to make? If they are asking you to make butyric acid, we know we are going to get 2 atoms from ethyl acetoacetate. So we are short of 2 acids here because butyric acid has 4 carbon atoms in it, and therefore we have to carry out the reaction with an alkyl halide which has 2 carbons. Similarly, if they give you valeric acid. Now see, here we've complicated the question for you. Valeric acid. What is valeric acid? Valeric acid is an acid which have 5 carbons in it, and there they have given you the common name. They have not given you the IUPAC name, that is converted into pentanoic acid. So you have to know common names of certain acids, like what is formic acid, acetic acid, propanoic acid, butyric acid because it is present in rancid butter, acetic acid it is present in vinegar. Then we have valeric acid, and then you have caproic acid which is having 6 carbons in it. It is present in the capricorn, that is goats. So that is how you can remember the name of these acids. So if I tell you that convert it into valeric acid, so you have to remember that you are getting 2 atoms from ethyl acetoacetate. Valeric acid has 5 carbons in it. So what is the alkyl halide that you will use? 5 minus 2 is 3. So that means we will be using propanoic halide. Similarly, if they ask us to make caproic acid, we know it has 6 carbons in it. So 6 minus 2 gives me 4. So I'll be using butyl halide there. Right. So now let us get back to the discussion as to how we will prepare butyric acid. So when you carry out the reaction of butyric acid in one's first step, that is, you will convert it into its sodium salt. And this sodium salt on reaction with ethyl iodide will be converted into alkyl derivative. And this ethyl acetoacetate on acid hydrolysis will give us butyric acid. Here now I have shown you the mechanism of this reaction. So in the first step, what is happening? Ethyl acetoacetate is reacting with sodium ethyl oxide, resulting in the formation of sodium salt of ethyl acetoacetate. In this case, since the bond between carbon and hydrogen is weak, so this hydrogen is given off as proton, that is ethyl oxide anion picks up this proton and is converted to ethanol, and in turn methylene group having a negative charge on it, that is the ester anion, reacts with the sodium to give us sodium salt of ethyl acetoacetate. This I have all shown you on your screens. Now in the second step, look carefully at the screen. What is happening, that this sodium salt of ethyl acetoacetate now reacts with ethyl bromide. Now carbon being more electronegative, the methylene carbon being more electronegative, as I've already said that this molecule is, now this bond is ionic in nature, that is the bond between the carbon, methylene carbon, and the sodium, because you can see that the methylene carbon has a negative charge on it and sodium has a positive charge on it. So this will now act as a nucleophile through negative charge on methylene carbon and make a bond with ethyl group, that is with the alkyl group, which is having a positive charge on it. Why is this alkyl group having a positive charge on it? Because bromine being more electronegative will pull the electrons towards itself. And since it pulls the electrons towards itself, this carbon has a slight positive charge on it, and in an SN2 mechanism, this methylene group makes a bond with this carbon from the backside. Sodium picks up, sodium being positive, will pick up Br minus, resulting in the formation of sodium bromide. And now what we are getting here is, we are getting a monoalkyl derivative of ethyl acetoacetate. That is, we are getting a ethyl derivative of ethyl acetoacetate here. Now what is done here is, that is acetic hydrolysis is brought about, and when you bring about the acidic hydrolysis, what do you find? That the H, we have to look into the two water molecules here. One of water molecules will break up into OH, and OH will go on to the carbonyl carbon of the acetyl group. H will go to the methylene group. And in the second case, again, what will happen? OH will go to the carbonyl group because this carbonyl group is electron deficient, and H will go on to the ethoxy group. And what will we get here now? Acetic acid and ethanol as the side products, and you will get butyric acid. So what you have to now remember here is, I am repeating again, that is when we are carrying out the acid hydrolysis, and this is final, you have to remember this point, that when we are carrying out the acid hydrolysis, we will be using two water molecules. And what you have to remember is, the easy way of remembering is that you will break the bond between the carbonyl carbon and the methylene group, and between the carbonyl carbon and the ethoxy group. When you do so, you find that both the carbonyl carbons are electron deficient, therefore the OH will go on to these electron deficient carbonyl carbons, resulting in the formation of acetic acid. And then an H is going on to your methylene group. So this will be converted into CH3, CH2, CH2, COOH group. And in turn, H is going on to the ethoxy group, proton is going on to the ethoxy group, resulting in the formation of ethanol. So similarly, you can also prepare valeric acid. In my next lecture, now I shall be discussing the preparation of dicarboxylic acid. And for this lecture, I had consulted the books by Behl and Behl and Morrison and Boyd. Thank you.